When millions of gallons rush down a mountain grade, the destructive potential is massive. This physical force can easily carve through solid bedrock. That energy originates high above sea level. High elevation reservoirs lock away an immense volume of water, creating potential energy that scales with every meter dropped. The challenge is harnessing that static wall of water. At the bottom of that drop, the intense pressure can literally blow standard machinery apart. To survive that extreme environment, engineers rely on a highly specialized piece of equipment, the Pelton Wheel turbine. Unlike standard turbines that operate entirely underwater, the Pelton Wheel spins in open air. It operates by converting the immense static fluid pressure into pure kinetic velocity before the water ever strikes the metal. To understand how this machine captures energy, we trace the water's precise path from the mountain peak down to the exact point of mechanical impact. This schematic shows a hydroelectric plant's footprint. It begins at the reservoir, or head race, at the top. It concludes at the bottom discharge, the tail race. The massive vertical drop between these points provides all the system's potential energy. Every pipe, valve, and tunnel in this entire structural layout exists for one purpose: to deliver that potential energy to the turbine floor while losing as little of it as possible. The critical delivery conduit bridging the dam and the turbine is the penstock. These heavy-duty steel pipes carry the water down the mountain. Looking back at the layout, the total theoretical elevation drop from the reservoir surface down to the turbine nozzle is called the gross head. But theoretical energy doesn't perfectly translate to reality. As water rushes down miles of penstock, it grinds against the internal walls, creating friction loss. Subtracting that from the gross head gives the net head, the actual usable pressure arriving at the turbine. This delivery system contains a catastrophic vulnerability. If the turbine suddenly needs less power and restricts the water flow, the massive kinetic energy already moving down the penstock creates a deadly pressure shockwave called a water hammer, which can rupture the steel. To prevent a blowout, engineers install a surge tank. This is an open-air vertical pipe connected to the penstock that acts as a failsafe. It absorbs the shockwave by allowing the excess water to safely surge upward against gravity. The penstock and surge tank successfully deliver safe, high-pressure water to the plant floor. But static pressure alone cannot turn a Pelton wheel. This brings us to the exact boundary between the pipe and the spinning turbine, the nozzle. It serves as a mechanical choke point, taking the static pressure of the net head and forcing it through a tight opening to create a high-velocity kinetic jet. But a power plant faces a constant operational hurdle. It must continuously adjust its electrical output to match the fluctuating power demands of the city grid it supplies. The operators cannot simply lower the water's velocity to generate less power. Dropping velocity destroys the turbine's momentum and efficiency. To lower the power output while keeping speed constant, they have to reduce the volume of water hitting the wheel. Engineers control this flow using an internal component called the spear. By sliding back and forth inside the nozzle, the spear adjusts the internal geometry of the opening. The physical movement of the spear alters the total discharge area, controlling the flow rate. Meanwhile, the actual velocity of the water remains constant, dictated entirely by the net head and the specific mathematical coefficient of the nozzle. Thanks to the spear, the turbine is struck by water at the optimal speed, regardless of how much total power the plant is generating. We can now follow that optimized jet out of the nozzle and into the heart of the machine, the runner. The runner is lined with a series of highly specific double-cupped buckets. Notice the exact point of impact. The water jet doesn't hit a flat surface. It strikes precisely on the sharp, raised center edge of the bucket. This sharp edge is called the splitter. If the massive force of the water jet pushed even slightly off-center on a flat blade, it would generate an asymmetrical load. This creates axial thrust, a lateral force so strong it would shear the turbine shaft right off its bearings. The splitter completely neutralizes this threat. It slices the incoming jet perfectly in half, forcing the water through twin U-turns. Because the water exits evenly to both sides, the lateral forces perfectly cancel each other out. The splitter serves as a structural safeguard, allowing the machine to survive the mechanical stress of its own output. Looking at this runner assembly, how do engineers determine the exact number of buckets? If there are too few, gaps are too large. The jet shoots straight through and kinetic energy is completely wasted. But if you pack too many buckets onto the wheel, the water violently collides with the back of the adjacent buckets as they spin away. This creates massive friction losses, destroying the turbine's efficiency. To find the perfect balance, engineers use the jet ratio. This is calculated by comparing the overall diameter of the massive runner wheel to the tiny diameter of the water jet striking it. Using an empirical calculation known as Tagan's formula, they plug in this ratio to determine the exact optimal bucket count for that specific power plant. The physical form of the Pelton wheel leaves no room for guesswork. Its design is governed by strict mathematical boundaries, ensuring absolute maximum momentum capture. Once the plant needs to shut down and the water supply is cut off at the nozzle, one final problem remains. How do you stop a massive steel wheel that is spinning with immense rotational inertia? The answer is a secondary control system built into the top of the housing, the brake nozzle. It fires a smaller, secondary jet of water directly onto the back of the spinning buckets, fighting the turbine's momentum to force a rapid halt. Finally, we can look at the outer casing that encloses the entire turbine operation. Unlike a submarine hull or a submerged reaction turbine, this casing is not built to hold back extreme hydrostatic pressure. Because the energy conversion already happened at the nozzle, the casing's only job is to stop water from splashing everywhere and safely guide the spent, zero-energy fluid down into the tail race. The Pelton wheel represents the precise management of kinetic energy, converting a mountain's water supply into grid-scale power through optimized geometry and raw physics.